That's great. Yeah. It's just one grade though, so I'm not ready yet because I have to see everything tomorrow. Is the question on here? All right, let's talk, guys. Come back to me. 5, 4, 3, 2, 1. All right, so I really heard some great conversation. You're doing a great job of trying to like justify your answers, which is marvelous. Okay, so let's just check and make sure we're on the same page. So we have this is number 2. This is not 2 coefficient. Okay, so we have this guy reacting. We have it's what kind of reaction, endo or exo? Endo, and it's making 2 gaseous products. So we have 1 mole of a gas here, and we have 2 moles of gas here. So that might be relevant. We'll see later on. Okay, so if you increase temperature, essentially I increased a what? A reactant. We're just going to call it a reactant. It's not truly a reactant, but it is forcing the forward reaction to occur at a higher capacity. So if you increase a reactant, your job is to get rid of that reactant, right? How do you do that? You shift right, because in that process of shifting right, you consume reactants, so they go down in quantity, and the products go up in quantity to help reestablish equilibrium. Okay, increasing volume. Show me the box. Increase volume. What happens to pressure? Decreases. Oh no, I have too few collisions, right? So the real problem here is an increase in volume causes a decrease in pressure. So you've identified the stress as low pressure. Well, that doesn't really ring a bell here with the whole reaction system. So think of it as too few collisions. So what's your job? You have to find a way to make more collisions. Which side's going to give us more collisions? The product side, because they have how many? They have 2 moles of gas, which is bouncing around twice the amount at that 1 mole of gas would be bouncing around. So that again would be a shift right. Adding helium, no shift, right? That's going to be because it's called an inert gas. Inert gases are non-reactive, and also it's not present in our equilibrium system, so this will be a no shift. Okay, adding carbon monoxide, which is basically you're adding a what? You're adding a product. Good. So if you add a product, how do you get rid of product? Shift left. So you should be shifting the opposite direction. Okay. Adding heat to the reaction vessel, which just means like the flask that this is all contained in together. That should be the same as what? Say again. Should be the same as A, because heat or energy should be relevant, or temperature should be relevant to the same thing. So in that case, which is energy, and that would be a shift right. Okay. You got a 5 and 5. Okay, so just give me like how many you got right on your hand. 5. Okay, we're doing all right. Let's keep rolling. Number 3, decrease the temperature. What's up? Shift left, shift right. Okay, so temperature is essentially energy. We're going to opposite direction. Whenever you add it on one side, you want to go the opposite direction to get rid of it. So that's a shift left. I'm sorry, decrease. Sorry about that. Did you guys say shift left or shift right? You shift right. Okay. Decrease in the temperature means that you don't have enough of this, so you want to make more of it. Therefore, we're going to go to the right. Okay, increase the volume. Okay, so what did you guys do? You looked at moles, right? So this is moles of gas. How many moles are over here? 3 moles of gas. And over here, 2 moles of gas. Okay, so if you increase the volume, what does that do to pressure? Decreases pressure. So there are few collisions. So that's our problem. There's too few collisions. How do I make more collisions happen? Shift left, because there's more moles of gas on the left side than the right side. Okay, adding oxygen, O2. Here, will you crack that door so I don't hear what's going on inside? Adding O2. Okay, so everybody says shift right, I think. And that's because you're adding a reactant. And so if you add a reactant, you got to find a way to get rid of it. So you react it away by going to the right. Heating reaction vessel. Good, so it's the opposite of A, because this one says decreasing energy. This is essentially saying increasing energy, so we're going to go the opposite direction. So increasing energy wants to go the opposite way so that we can get rid of it. Increasing pressure. And that's also the opposite of number B, because this was a situation where pressure would decrease. Increasing pressure, we are going to then favor the lesser moles, because lesser moles will fix the problem of too many collisions. All right, where are we at on out of 5? You have to participate in my survey. All right, let's do one more together. Check this out. So we have a reaction, pull the vessel, and now I want you to hold with your left or right hand on this one, okay? And if it's neither, but like this, okay? So go ahead. You're answering with your left or right hand. You've already done this, so go with what you answered. All right, a lot of us are saying shift right, okay? So cooling the vessel means you're decreasing this, so you want to make more of that to accommodate or alleviate that stress. So that's a shift right. Keep going, increase the volume. So I've got some mixed results here. So if I increase the volume, what does that do to pressure? Decreases pressure, and that's like Boyle's law, right? So then I go here and I count, how many moles of gas do I see? 5, and over here, no. Moles of gas, there's only 2. I know it's the same situation more or less, but this is a liquid, so it's not going to cause any significant pressure issues, so we don't want to count for that. So there's 5 moles of gas here, 2 moles of gas here. Low pressure basically means too few collisions. So if you want to find a way to increase collisions, which way do we go? Left. We want to go opposite the 5 mole side, which would go more collisions. Adding sodium chloride. No shift, good, because it's not present in our equilibrium system, and it's not a common ion because there's no aqueous systems here for us to even add ions. Adding neon. No shift because it's also not present in our equilibrium system. It's an inert gas. Increasing pressure. So the problem is too many collisions, right? We want to go to the lesser moles. So the lesser moles would be 2 moles. Good. You guys are awesome. Okay, so we're going to apply one more of these together. I think I printed this for you. Yeah, it's number 14. Oh, hold up. Nope, lies. Here, no, it is. Number 14. Okay, so you have a reaction, and it's got a slew of examples. But in this case, we're not just saying, oh, is it shifting left or shifting right? We're looking for the effect of that. So, like, when I shift left or when I shift right, what's going to happen to each of these reactants and products? So, talking to your groups on number 14, go for it. I decide.
Oh, no. So it's the same thing. So it's
All right, let's check the first two rows. Some of you guys are getting the hang of it. And come back to me, 3, 2, 1. You will absolutely see a question like this tomorrow on your 20-question multiple choice cumulative test between acid base and collision theory equilibrium, where it's like, hey, I've added this. What's going to happen? So your job is to decide the shift, and then because this happened, what's going to happen to the concentration of reactants and products? So basically, this would be like in form of multiple choice. Like, what would happen to nitrogen monoxide upon adding P in 503? And so your job is to think shift first, and then say, okay, what's the impact of that shift? So we have this being added, and if I add this, what's going to happen? What kind of shift? Okay, so that's a reactant, right? So as we increase reactants, it's going to shift right. Okay, so if we go to the right, what should happen to both of these? Right, they get consumed. They should both go down. So carbon monoxide should go down, and PN5O3 after the shift, right after the reaction has gone to the right, will be lower than it was before. So it should go down. What should happen to both products? They both should go up, because as you go to the right, you consume reactants, you form products. So that should be up and up. Okay, adding C3PO, thought that was pretty good. Okay, adding C3PO, what kind of shift is going to occur? Everybody, come on. It's going to go to the left because C3PO is a what? Good, good. As you add a product, it's noticing you're increasing this side, so you're going to go the opposite direction to accommodate for that. So what should happen to both reactants? Say again? Line problem? Up. Okay, so both reactants should go up and up because we're going to be shifting left, which means we're making more of them. But in order to make more of them, what happened to both products? They go down, right? Law of conservation of matter still applies every single time here. So these should go down in order to accommodate. Okay, let's keep going. Carbon monoxide was removed. Okay, so once you know the shift, you guys should be able to get the idea of concentration changes. But what's happening here? What kind of shift? Okay, so as you decrease a reactant, we want to make more of that because we need to get it back up to where it once was, and that's going to be a shift left. Okay, nitrogen monoxide was decreased. Okay, so as you decrease a product, it's going to need to be made more of, so you need to find a way to get that way, which is a shift right. And pressure was increased. So I heard two people say shift left. Let's talk that one out. Pressure was increased. So what's our problem right now? Too many collisions. We have too much stuff, right? So do I want to go to side with more stuff or less stuff? Less stuff. That means less gases, right? So we have 3 moles of gas plus 1 mole of gas, so that's a total of 4 moles of gas. And then we have 1 plus 5, so that's a total of 6 moles of gas. So that's definitely going to be a shift left because you want to find a way to go to the lesser moles. Give me a double thumbs up if you're okay with this so far in terms of interpreting a little farther. Okay. I see a couple of us need a little bit more support there. Let's look at one more with an example of, hold on, let me show you guys this. This is above where you were just working, right? Come up with, if you can, 5 ways to increase or to shift the equilibrium towards the products, okay, for that specific example. Do that out loud at your table, talk it out. Coles table. Anonymous table, you guys get grab your little cups. Alright, get logged on to my website whenever you get there, and then we're going to talk about number 1 and 2 up here. Alright, and come back to me. 3, 2, 1. Anonymous table, give me one type of shift or stress we could cause a shift towards the products with.
Decrease to an.
Okay, so decrease, I'm just going to say the product, so not the two. So nitrogen dioxide. Just trying to use our nomenclature where we can. CJ's table? Sorry, I'm going to verify. He's saying decrease the concentration of N2O2. Go ahead. Increase the volume. So increasing the volume means you want to go for more moles of gaseous products. So increasing the volume, good. Nope, got that table already. Current table. Okay, so increasing volume is also analogous to saying a decrease in pressure. So that's going to cause too few collisions. This is going to give us more moles of gas. Great fix. Cold stable. Nope, dang it. Corbin stable. Say again? So, you're good. So this right here, this is the point I really want to make. This is a what kind of process, endo or exo? So do you guys see the positive value here? What does that mean again? It's endothermic, right? So this is an endothermic reaction. Just because it's very separated, it's not saying, hey, I'm a product. It's just separated to indicate the delta H or the enthalpy of the reaction. That really means that energy is added as a reactant. So like Maverick said, increasing energy will help us shift the forward direction. So adding energy. And when you say that, what do you really mean? You're adding what? So maybe adding heat. So you're heating the reaction vessel. Okay? All the same tables. Wesley's table. So adding nitrogen, or say that for me again. One more time. Tetroxide. Good. Dinitrogen tetroxide. So adding that reactant would cause a shift towards the products. Is there anything else, guys? Is there? Did I exhaust all yours? Your examples? Guys, calm down. Like, you can't be talking this much.
Yeah.
Thank you. Okay. All right, let's do this one from our heads then. No collaboration, okay? So if I call on you, give me a response, please, okay? Bryce, give me a way to shift towards the products on this one. Adding oxygen gas, so increasing the concentration of oxygen gas. Keep going, Kendall. One more time. One more time. Decrease energy. So this one is XO. So that means that energy is essentially a product. So decrease energy is a great idea. Not. So remove, what's that product? Nitrogen what? Monoxide. Good. Ariel? Okay, so hold on. Well, look, actually, I'm looking at it now. What do you notice is the number of moles on both sides? They're both 2, right? So we got 2 moles of gas, 2 moles of gas. So what's not going to cause any shifting? So pressure won't work and volume won't work. So both of those are out of the picture. So we can't say those. Camilla? Yeah, me too. Okay, thank you. All right, so go to my website. Oh, the other reactant. Sorry, I was thinking reactants in general. So N2 concentration can go up. Squeezing in there. We good? Okay, so go to my website, go under Unit 8, and I'm going to tell you guys a couple things before we get started. We have to review a little bit of the study guide, but I'll do that after you guys get the last bit of Le Chatelier's principle practice in. But you're going to the Honors Chem virtual lab, and that virtual lab is under Unit 8. And you have to hit more because it's not currently visible, so you hit more under Unit 8 and Honors Chem Le Chat virtual lab. So it's a Word doc, so go ahead and get that pulled up. And what I'm expecting you'll be capable of, and I guess I'm going to show you one more thing too while you're with me, is you're going to do a couple of parts. There are like 7 different chemical reactions that are present on this virtual lab, maybe 8, but I'm going to have you start with 2. You get the hang of it and you're good to go. I'm going to shift modes after that so you can actually have some time for review, maybe knock out some of that red and yellow, okay? So when you get there, you have to complete the background. There's a little bit of background reading, and there's like maybe a couple of questions that are related to it that are in the pre-lab. So 1, read the background. 2, complete the couple pre-lab questions. 3, make this table, and this table is simply like you name the system you're speaking of, like the chemical reaction you're speaking of. You're writing down the stress that's provided for you from that simulation. Like they will give you every single stress, and so the first one I've kind of given it all to you so you can see it all laid out. You're writing down the color change that's relevant to that shift. You're deciding which way it shifted, and you're explaining why. You're just giving like a really simple explanation why. Don't write me a paragraph. But you're going to do that for 2 systems. Like I said, there's like 7 or 8 on there. So you're going to do it for the cobalt system and then the copper system. After that, there are a couple post-lab questions. Like I said, we'll kind of see where we are when we get there. But what's really important to write down is the BCE with the colors of the reactants and products. You won't, when it turns purple or it turns blue or it turns clear, you won't really know what that means unless you know which side reactants or products is purple or blue or clear. Okay, so are we on that document? Yes? All right, so I'm going to make sure you can navigate. So when you get here, go ahead and just, control click, and it's going to bring you up to the main page first, the home landing page. So if you're working with me, you can kind of get to the same place I am. This is not relevant yet, so we're going to go to the one that says equilibrium and Le Chatelier's principle, which is like the 5th one down on the left. And this is where your landing page is. So the intro is literally already here. So in this experiment, you'll be introduced to chemical equilibrium. You'll be presented with a number of systems. You'll ask to stress them, and by changing the concentrations of reactants or products, or by changing the temperature, that's you stressing the system. So then you'll click the background. The background is just a little bit of reading. There's some extra links there if you need some more information. But that's just a little bit of reading. You're not really writing anything down right now for that. I know in the lab protocol it says, feel free to write a couple of bullet points down. You're good. You can read that. Okay? But the pre-lab information is what you'll start together. Okay? And I do think it's very relevant to know the colors. So it tells you, like, an example, the test tube on the left contains only copper, and you can see, or copper 2 sulfate, and you can see that color is like a teal blue. And on the right, some potassium bromide has been added, and you can see that it's making CeBr4 2- ion, which is green. So you'll see colors. So make sure you know which color represents what. Okay? You are feel free to work in groups of 2 if you would like to converse with someone. If not, knock it out by yourself. Okay? You guys can see the instructions right here again. This is what I'm expecting of you. You can move or rearrange yourself some, but Jam has some. You have 3 lab questions, and you're drawing the little results table.